Welcome to the Deep Dive. Today we're tackling Kolmogorov complexity.
Yeah.
Think of it as this really core way to measure the true information inside a string of data. It could be anything, right? Code, DNA.
Anything digital, pretty much.
Exactly. And it's not just about counting the bits. Kolmogorov complexity asks a deeper question. What's the absolute shortest computer program you could write that generates that specific string?
That's the heart of it. It's all about the algorithmic information content. It's an idea that popped up kind of simultaneously in the 60s.
Oh, right, from two different people.
Yeah, independently. You had G. Chaitin, who was actually an undergraduate at the time in 1965.
Wow.
And the very famous Andrei Kolmogorov, also in the 1960s. The main groundwork, the sort of foundational properties, those were really nailed down in the 1970s.
Okay, so we've got a stack of readings on this really interesting stuff, and our mission today is basically to pull out the most intriguing bits for you, maybe some surprising angles on Kolmogorov complexity.
Sounds good. Where should we start?
Right, let's dive in. The core idea seems to hang on this concept of a description mode, or sometimes called a decompressor.
Exactly. A decompressor is just, it's a computable function. Think of it like a program that takes some other program, usually a shorter one, as its input.
Okay.
And it outputs the original longer string we're interested in.
So for any given string, say a sentence or a sequence of numbers, there might be loads of different programs that could produce it.
Oh, absolutely. Some might be really long-winded, others super elegant and short.
And that's where the complexity comes in.
Precisely. So if we pick one specific decompressor, let's call it D, just for discussion, then the Kolmogorov complexity of our string x with respect to that D, written C sub D sub x,
Right.
is simply the length of the very shortest program, let's call it Y, that makes D output X. So dy equals X. It's all about finding that minimal description.
The most concise set of instructions, basically. Okay, but what if a string can't be made by a particular decompressor D?
Good question. In that case, we just say its complexity relative to D is infinite.
Ah, okay. No finite program within that D system can produce it?
Yep.
This choice of decompressor, D, seems really important then. How much does it actually matter which one we pick? Does it completely change the complexity number? This feels like a potential catch.
It is important, and you're right to ask. The value C sub D sub X definitely depends on the specific D you choose. But, and this is a really key insight, there's this idea of an optimal description mode. Let's call it D sub 0 sub.
Optimal. How so?
An optimal D sub sub is essentially universal. It's so powerful it can simulate any other computable decompressor you can think of.
Whoa. So it can run simulations of other description methods.
Exactly. And crucially, it can do this with only a constant amount of extra code, a small fixed overhead in the program length, regardless of the string X.
Like a universal translator for computational descriptions.
That's a great way to put it. And because of this, the standard definition of Kolmogorov complexity, the one people usually mean when they just write CX without a subscript,
Yep.
is understood to be defined using one of these optimal universal D sub 0 sub machines.
Okay, so we sort of agree to use a best possible decompressor as the standard.
Pretty much. And this leads directly to something called the invariance theorem. It might not always be called that explicitly in text, but the idea is fundamental.
What does it say?
It says that if you choose any two optimal description modes, say D sub 0 sub and D sub sub, the Kolmogorov complexity you calculate for any string X will only differ by a constant value.
So C sub 0 sub X might be, say, 100 bits, and C sub D sub X might be 105 bits. But that difference of 5 bits doesn't depend on X itself. It's just down to the specific optimal machines.
Exactly. The difference is bounded by a constant, a 1 in the notation. This is huge because it means the fundamental algorithmic information content we're trying to measure is robust. It doesn't wildly fluctuate based on reasonable choices of our computational model.
That is reassuring. It makes the whole concept feel much more solid. Okay, so given this definition using an optimal D sub 0 sub, what are some basic properties of CX?
Well, one very basic one is that the complexity CX can never be much larger than the actual length of the string X, which we write as LX.
How much larger?
Only by a constant amount, so CX, LX plus O1.
And why is that?
Think about it. You can always have a decompressor that simply takes the string X itself as the program and just outputs it directly.
Ah, like the identity function. the program is just print the string itself.
Exactly. The description is just the string, maybe with a tiny instruction prefix. So a string can't be fundamentally more complex than its own literal representation, plus a little bit.
Makes sense. What else?
Another really important one is often called the non-growth of complexity under algorithmic transformations. It sounds fancy, but the idea is simple.
All right.
If you have some algorithm, some computable function A that takes a string X and transforms it into a new string AX.
Like reversing a string or calculating a hash or something.
Any computable transformation. Yep. Then the complexity of the output, CAX, can't be much bigger than the complexity of the input, CX. Again, it's bounded by a constant, CX plus O1.
So applying an algorithm doesn't magically create a whole load of new fundamental information. It mostly just shuffles or extracts what was already there, information-wise.
That's the intuition, precisely. The core algorithmic information doesn't significantly increase just by processing it.
And that lets you apply this complexity idea to things beyond just strings, right?
It does. Because if you can encode other finite objects, integers, graphs, maybe even simple images as binary strings in a computable way, then you can talk about their Kolmogorov complexity via their string encoding. The principle holds that the underlying complexity is captured regardless of the specific encoding up to these constant factors.
Okay, interesting. Now, the readings also brought up conditional Kolmogorov complexity. What's going on there?
Ah, right. See, pourquoi? This is a neat refinement, it asks. What's the length of the shortest program that generates X, but this time the program gets Y for free as an additional input?
So it's like saying, assuming I already know Y, how much more information do I need to specify X?
That's exactly it. It measures the information content in X that isn't already present in Y.
So CY would be small if X is easily derived from Y.
Precisely. If Y basically tells you how to get X, then CY will be small, close to 0 perhaps.
And the readings hinted there's a relationship between this conditional CHI and the regular CX and CY.
Yes, there are important relationships, like how CXY, the complexity of the pair, relates to CX and CIX. It ties into information theory concepts. The full text probably delves into that chain rule for complexity.
Something to maybe explore another time. This stuff connects out to other big ideas too, doesn't it? The readings mentioned randomness, probability.
Oh, definitely. Big connections were made, again, mainly in the 70s. C.P. Schnorr, and also L. Levin, who was actually one of Kolmogorov's students, they found this deep link between Kolmogorov complexity and what's called algorithmic randomness.
Algorithmic randomness. What's the quick idea there?
It's a way to formalize what it means for an infinite sequence of bits to be truly random. P. Martin Luff developed this idea. Intuitively, a sequence is random if you can't compress it, if its Kolmogorov complexity is high.
So high complexity means more random.
Essentially, yes. A truly random sequence can't be generated by any program significantly shorter than the sequence itself. Kolmogorov complexity gives you the mathematical tools to make that precise.
And there was another type of complexity mentioned there, monotone complexity.
Yeah, that came up in the context of this randomness connection. It's a slightly different flavor of complexity, useful for technical reasons when dealing with potentially infinite computations or approximations.
Okay. And what about probability? Solomov's name came up.
Right. Ray Solomonoff had these pioneering ideas about a priori probability, basically, trying to assign an objective initial probability to any given hypothesis or string before seeing any data.
How likely is something, just based on
Right.
what its description?
Exactly. His idea was that simpler explanations, shorter programs, are inherently more probable. This intuition was later formalized, again by Levin and also Chaitin, using something called prefix complexity.
Prefix complexity, is that different from the standard CX?
It's subtly different in its definition, using prefix-free codes, which we might get to, but it turns out to be very closely related to CX. The key thing is that it provides a rigorous way to define this a priori probability based on description length.
So these different versions, plain complexity, CX, monotone, prefix KX, they're all tools developed to tackle slightly different aspects of information, randomness, and probability.
You got it. And they've proved incredibly useful, not just in theoretical computer science, like studying computability, but also in probability theory, statistics, even philosophy of science sometimes.
The readings mentioned using it to study algorithms for the halting problem. That sounds paradoxical, since the halting problem is unsolvable.
It does, right. But it's used to study so-called generic algorithms or properties related to the halting problem. More fundamentally, though, there's a deep result. Kolmogorov complexity CX is itself uncomputable.
You can't actually write a program that calculates Cx for any given x.
Nope. If you could solve the halting problem. The reasoning is a bit involved, but it shows a fundamental limit. We can define this measure of information, but we can't, in general, compute it.
Wow, that's a mind bender. So this field is still active.
Very much so. If you really want to dive deep, the monographs by Andre Nees or the one by Rod Downey and Dennis Hirschfeld are excellent, though quite advanced resources.
Good to know. Okay, let's shift gears slightly. We've talked about measuring information. What about the sets of things algorithms can produce? The readings use the term computably enumerable sets.
Right, or just enumerable sets, a set of finite objects, strings, numbers, whatever is called enumerable if there's an algorithm, a program that takes no input
Okay.
that will eventually print out every single member of that set. It might print them in any order, there might be delays, it might even print duplicates, but crucially, every element in the set will eventually appear on the list.
Okay, so there's a procedure that guarantees to list everything in the set, eventually.
Yeah.
But the reading made a point that this algorithm doesn't have to stop, even if the set is finite. That feels weird.
It does seem a bit strange at first, but it's a key part of the definition in computability theory. Think about searching for something. You might have an algorithm that searches and searches. If the set of things it could find is finite, it might find them all, but the searching process itself might be designed to run forever, just in case there's more.
Ah, so the process guarantees eventual inclusion, but not necessarily termination. It covers all bases, even if it keeps looking pointlessly afterwards.
Exactly. It separates the property of being able to generate all members from the property of knowing when you're finished.
Got it. Now, another term that seemed important was prefix-free encoding. What's special about that?
A prefix-free encoding is a way to represent strings, let's say converting objects A, B, C into binary strings, code A, code C, with a special property.
Which is?
No encoded string is the beginning part, the prefix of any other encoded string in the same set. So code A cannot be the start of code B, and vice versa.
Why is that useful?
Imagine you concatenate two encoded strings .code followed immediately by code B. Because no code is a prefix of another, as you read the combined string from the beginning, the instant you complete a valid code word, say code A, you know for sure that's the end of the first item.
Ah. So you can uniquely chop up a long stream of concatenated codes back into the original pieces without needing special separators.
Precisely. It allows for unique and immediate decodability. This is super important in data compression, like Huffman codes. And as we mentioned, it's the basis for prefix complexity KX, which connects to probability.
Okay, that makes sense. This is all quite intricate. Let's tackle this busy beaver function now. It sounds fun, but probably isn't.
Huh. It's definitely a theoretical construct. The busy beaver function, usually written BBN, is defined using Turing machines.
Okay, the theoretical model of computation.
Right. It represents the maximum possible number of steps that any n-state Turing machine can run for, starting on a blank tape before it halts. We only consider machines that do eventually halt.
So for any given number of states n, there's some specific maximum runtime among all possible halting machines of that size.
Yes, although calculating BBN is itself famously difficult and grows incredibly fast, it's another uncomputable function, in fact.
Uncomputable again. Okay, so how does this connect back to Kolmogorov complexity?
The connection is quite surprising. The readings state that if you take any number t that is larger than BBN, then the Kolmogorov complexity of t itself, CT, must be at least n minus some constant.
Whoa, so a number vastly larger than the busiest n-state machine's runtime cannot have a short description. Its complexity must be high, related to n. How does that work?
The intuition is a proof by contradiction. Suppose you did have a very large number t, much bigger than BBN, but it had a very short description, say a program of length k, where k is much smaller than n.
Okay.
Then you could potentially use that short program of length k, along with the value n, to construct a Turing machine with roughly n states that simulates the short program to generate t, counts up to t, and then halts.
Right.
But since t is larger than BBN, this machine would run for more steps than any n-state machine is supposed to be able to before halting.
Ah, so you'd have built an n-state machine that violates the definition of BBN as the maximum runtime.
Exactly. That's the contradiction. Therefore, the initial assumption must be wrong. A number t much larger than BBN cannot have a description significantly shorter than n. Its complexity c must be at least n01.
That's really clever. It links the limits of computation duration with the limits of description length, and subtly reinforces the uncomputability of CX2 since BBN is uncomputable.
It all ties together in these deep ways.
Okay, one last specific connection to nail down. We mentioned prefix complexity, KX, used for a priori probability. The readings mentioned a direct comparison, KX ECX plus O1.
Yes, that's a fundamental result. Despite their different definitions, one using prefix-free programs, the other using any program on an optimal machine, plain Kolmogorov complexity CX and prefix complexity KX are essentially the same, up to an additive constant.
So for most practical purposes, thinking about the information content, they give you roughly the same measure.
Pretty much. The O1 difference is often negligible when you're talking about the complexity of large strings, but KX, the prefix complexity, is the one that properly formalizes Solomonov's idea of a priori probability.
Not so.
Because prefix-free codes have this property that the sum of two sublength program over all valid programs converges. It doesn't go to infinity. This lets you define a probability distribution where px is related to 2's kx up. Shorter programs, smaller kx, correspond to exponentially higher probabilities.
So prefix complexity gives a direct mathematical route from the shortest prefix-free program generating x to the inherent probability of x arising from a computational process.
That's the core idea. Simpler explanations, shorter prefix-free programs are exponentially more likely a priori.
Wow. Okay, this has been quite the journey through some really foundational concepts. As we sort of start to wrap up, what's a final thought we can leave our listeners with? Something to chew on.
Well, maybe consider the really deep implications of having a measure of information of complexity that is fundamentally tied to computation. What does it really mean for something, maybe a physical process or a biological structure, to be complex in this algorithmic sense?
Yeah.
Are there absolute, unavoidable limits to how concisely we can describe the world, even in principle, dictated by the laws of computation? And maybe how does this whole idea of Kolmogorov complexity challenge our everyday intuitive notions of what it means for something to be random versus structured?
Does true randomness even exist if complexity is always relative to a computational model? Heavy stuff.
It definitely pushes you to think differently about information itself.
Absolutely. Well, we've really only scratched the surface today, as you can probably tell. These connections run deep into computability theory, information theory, probability, and beyond.
There's a lot more there.
For sure. We definitely encourage you, if this sparked your interest, to maybe look into some of those resources mentioned, like the books by Nies or Downey and Hirschfeld, or related research, to explore further. Understanding Kolmogorov complexity, even at this level, gives you a powerful new lens for thinking about information and the ultimate limits of what we can compute and describe.
Agreed. It's a fundamental concept.
Thanks for joining us for this deep dive.